Okay, I'm back. So let's continue. Yes, so correctness is basically to implement all the functionalities of the system correctly. Okay, so this is a very important attribute of a good software design. The second attribute that we will be talking about is understandability. All right. Now, what is understandability? That means in a design, a design should be such that it should be easily understandable, right? What do you mean by understandable? That means if anybody has a look at the design, right? If, for example, why it has to be understandable is because your design is going to be used by multiple developers who are going to refer to your design and write the code. So obviously the design should be crystal clear. It should be easily understandable. Now with understandable comes two different words. One is called as modular and the other one is called as layered. Okay, modular and layered. Now if your design is modular and if your design is layered, then automatically it is a design which is easily understandable. Now what exactly is modular and what exactly is layered, I will be telling you, in the next class, or probably, if we have time, in the same class itself. But for now, just remember that correctness, understandability are the two important characteristics of a good software design, and the third one is efficiency. Okay, third one is efficiency. Now efficiency means you should adequately address the resource, time and cost optimization issues, which means that your design should be such that it is, very optimal. That means you should not have a design which is very lengthy to implement. You should have a design with all the best practices. You should have a design which can be done in a shortest period of time. It should be a design which can be implemented in a very cost-effective way. That means all the optimization, if you've heard about optimization, means making things as efficient as possible. Okay, so a design should be optimized, right? And the final attribute of a design should be that it should be maintainable. What is the meaning of maintainable? That means a design should be such that it should be easy to change. Okay, so we talk about maintainability. That means a design should be easy to change. Now let me just tell you what exactly is a modular and a layered design. So I'm just going to draw a simple diagram, and through that I'll explain what exactly is a modular and a layered diagram. So we came across these two words, modular and layered, right? So I'm just going to show you a simple design and explain what exactly do they mean. Right. Let's say we have lots of modules. Let's say we have identified M1 as one of the modules. Then we have M2, which is another module. Then let's talk about M3. These are all the modules that I have identified from my SRS. Let's get in some more. So here is M4, and then we have M5, and let's talk about M6. Okay, let's stop here. So we have 6 modules in our software, and all these have been identified from my SRS. Now let's say these modules have some kind of relationship. They have some kind of relationship. That means one module may invoke another module. That they may be a control relationship amongst these modules. So let's say the module 1 can invoke module 2. Similarly, module 1 can invoke module 3. Similarly, we can have a scenario, let's say, where module 3 is invoking module 4, module 3 is invoking module 5, module 3 is invoking module 6, right? And again, between 4 and 5 there is another invocation, and 5 and 6 there is another invocation, and there is all possible kinds of invocation all over the place, right? We can have this also. Now if you look at this design, it's very complex because you have random invocation amongst all different modules, M1, M2, M2, M1. That means M1 is invoking M2, M2 is invoking M1. It's like, two different persons, kind of, they can control each other. Like I can say, go get a glass of water, and the other person will say, you go get a glass of, a packet of biscuit. So when you have a scenario like this, right, that means this is an example of very poor design. because it has got poor modularity. There's too many confusion here, too many, invocations across, right? There is poor modularity and there is no hierarchy. You know what's hierarchy? Hierarchy is basically there is no structure from top to bottom. Okay, it's everyone is invoking everyone. Now, this is a design which is very difficult to understand, right? Because if you look at it, too much of invocations and it's too confusing. So if I change the same design, let's say, I want to make a design which is nice, which is easy to understand, which this is not in a form of a layer or anything. You can't have an, kind of a top to bottom approach. You can't say that this is the topmost module, this is the bottommost module, because everyone is invoking everyone else. But say I change this design and now my design is such that here is M1, right? And this M1 is invoking M2, and then there is another, let's say a module M3, and then we have, let's say, M4, right? Like we have written in the diagram, at the side of this, and let's say we have M6. Now, we define the control relationship in such a way that, the topmost module can invoke the lower modules. You cannot have a lower modules invoking a topmost modules. So if you look at this diagram, it is too confusing because each module is invoking each one. But in this case, if you see, we have got a structure in place. Now what we have done is only the topmost module is able to invoke the lower modules. And again, this M3 is able to invoke M4, M5 and M6. Now if you look at this diagram here on the right hand side, right, you will find that it is arranged in the form of a layer. Look, this is the first layer. I can say this is layer 1. Then I can say that this particular, section M1, M2 and M3 are in layer 2, and the third one, that is this one, is a part of layer 3. Right? So now I have very easily separated this design into 3 different layers, and it is also hierarchical. That means at the top you have M1, then after that you have M2 and M3, and finally you have M4, M5 and M6. So there is a hierarchy. Okay, so such module or such design are actually called as modular and layered. So if you have a design which is modular and which is layered, has a good hierarchy, then this is an example of a good software design. Okay, it's very simple to understand. Now, layered design have certain, concepts added to it. We are going to talk about fan in and fan out. Now, fan in and fan out are concepts which are basically connected to the layered design, right? So, what exactly is fan out? So let's kind of understand what is fan in and fan out here. Now in a layered design, so here is my layered design, right? If you look at an invocation, okay, if you look at the invocation which is, which I'm highlighting between M1 and M2, right? This means how many modules are being controlled, how many modules are basically, for example, M2 is being controlled by M1 and M1 is controlling M2, right? So if let's take M3, that will be more clear. So in M3, how many modules are controlling M3? We have only one module which is controlling M3, which is this one. Let me just change the color here so that it's easier. Right, so if you look at this M3, M1 is controlling M3, and M3 is controlling 3 different modules, right? So this value 1 indicates that it is a fan in. So for M3 you have two, basically M3 you will have 2 values. One will be for fan in, one will be for fan out. What is fan, in? Basically, fan in indicates how many modules directly invoke a given module. How many modules directly invoke a given module. And fan out indicates how many modules a given module indicates. So for M3, how many modules does M3, invoke? So what is the number here? The number is 3. That means M3 invokes 3 different modules. So the fan out of M3 is equal to 3, right? Fan in indicates how many modules directly invoke a given module. That means M3 is invoked by how many modules? M3 is invoked by only one module, which is that? Which is M1. So what is the fan in value for M3? Fan in value is 1. That means fan in indicates how many modules directly invoke a given module. So a given module here M3, how many modules invoke M3? There is only one module. So what is the fan in value of M3? The fan in value is 1. How many modules does a given module invoke? So in this case the given module is M3. So how many modules does M3 invoke? So in this case M3 is invoking 3 modules, right? So the fan out value for M3 is 3 and fan in is 1. Alright, so if you look at M1, for M1 the fan in value is 0 and fan out value will be how much? This is 1 and this is 1, that means 2. For M2 the fan in value is equal to 1 but the fan out value is equal to 0. For M4 fan out 0, fan in 1, right? Similarly for M5 you have fan in of 1 and fan out of 0. Similarly for M6 you have fan in of 1 and there is no fan out, so fan out value is 0. Okay, now what is the significance of fan in and fan out? So when you have low fan out, right, that means it's a measure of the number of modules directly controlled by a given module. Now basically what happens is, like when you have low fan out, right, when you have low fan out it means, so for example M2 doesn't have any fan out, M4 doesn't have any fan out, right? So high fan out indicates code reuse. For example, if you have a high fan out, that means M3, right? Sorry, high fan in. I'm sorry. High fan in will represent code reuse. So if you have M3, how many fan in it has? 1. All these modules have 1 fan in. So let me just give you another example where then it will be clear. So suppose there is a module and there is a very high fan in. Okay, that means there is no fan out. Fan out is not there, but there are lots of fan in. So this module, that means fan in is high, right? So here is a module and fan out is equal to 0. Now if you have a very high fan in, it means that this module is being used by many other modules, right? M1, M2, M3, M4. That means so many modules are invoking M, which means that this is a representation of code reuse. That means this could be a library function. It is a library function means multiple modules are sharing that piece of code. That is why all the modules are connecting to this module. That means if you have a module M which has a very high fan in, it means that this module it consists of some common code which all the other modules want to use. Okay, so fan out indicates how many modules a given module invokes. Now M1 is not invoking any module. That means M1 is a module which doesn't need to invoke any other module. It is just a module which others are using it. So M1 is a classic this module M is a classic case of module which is like a library module. What are library modules? Library modules are those modules, right, which basically are used by other modules. It's like a shared module. Like for example, in every university there is a common library. Why is that library common? That means all the departments in that university can go and use that particular library because it has got all the common books. Similarly, when you have a module which has got no fan out, right, that means nothing is there. It is not invoking, it doesn't need to go and use or get something from any other module. It doesn't give any command to any another module. But all the other modules, like here, they are all using module M. This indicates, right, this indicates that a particular module is a library module. Okay, so high fan-ins are good. If you in a design, if you have high fan-in, that means you have done the design well, so that your code is being reused. So if I give you an example, and if I ask you to let me know what is the fan-in and fan-out of each different modules in a design, you should be easily able to tell me that. So if I give you a question paper in your exam, something like this, let's say, I'm just drawing it randomly here. So let's say if I give you a problem, this is M4, M5, M6, all random, okay? And these arrows denote invocations. And if I ask you to find the fan in and fan out of each of these modules here, you should be able to do it. So just for example, M1, what is the fan in? 0. What is the fan out? 2. M3, fan in is 1, fan out is 1. M6, fan out 0, fan in 2. So in all these cases, M6 is a module where module 2 and module 3 are sharing that M6 module. So this can be a library module. So M6 shows that there is code being reused. So M2 and M3 both are using the code from M6. Okay, so this is basically the concept of fan in and fan out. They are nothing but they are numbers which indicate how many modules are invoking a particular module and how many modules are being invoked through that particular module. Okay, so I think we can stop today's class here. We have got a good introduction to design. We have looked at the modular design. We have understood the concepts of fan in and fan out. And we have also seen what's a good modular design and a hierarchical design and a layered design, right? And we discussed some attributes of a good software design. And we also introduced design. And we also got to know that what's the difference between a high level and a low level design. And what are the activities that we need to perform in these two different design types, low level and high level. So if you have any questions, please let me know. You can ping me, you can message me or whatever it is, and we will get them cleared. So tomorrow we will start with 2 new concepts, and we will be bringing in cohesion and coupling. So we'll stop for today. Okay, see you. Bye bye.